Okay, section 4.6 talks about dimensions. Theorem 4.6.1 says all bases. Now remember the difference between spanning and bases. And I'll talk about that briefly after I talk about the first couple of theorems really quick and put everything in perspective. All bases for a finite dimensional vector space have the same number of vectors, meaning then if you find the basis for one vector space, you can't later on say, oh look, I missed one or I found an extra one. If that was the case, then the original wouldn't be basis. This is telling you that bases for a vector space are unique. Once you find them, they're set. That's it. You can't find any other or additional vectors. And the next couple of theorems will pretty much break that down. Let V be a vector. Let V be a finite dimensional vector space. And let those vectors like there form bases. Again, not span, bases. Those vectors have to be linearly independent and they must span vector space V. So we're not talking about a subspace, we're talking about bases. Now, A says if the set V has more than n vectors, then it is linearly dependent. Because if they form bases, that has to match the dimensions and they're linearly independent. Any additional vector must be a linear combination of those. And if set V has fewer vectors than n, so fewer n vectors, then it wouldn't span vector V, and therefore it wouldn't be bases or form bases. Now the dimensions, this is a notation we're going to use from now on. It says the dimensions of a finite dimensional vector space is denoted by the dimension of V and is defined to be the number of vectors in its bases. Now the zero vector space is defined to have a dimension of 0. If we're dealing with R sub n, so you know, 1 dimension, 2 dimension, 3 dimension, you must have that many vectors. So you know, for 1 dimension, for 2 dimensions, for 3 dimensions, and the claim is that any other vector can be written as a linear combination of those. This is R3, so we have 3. This is R2, so we have 2. This is R1, and so on and so forth. And if you're talking about a matrix, and the matrix happen to be an m by n, then the standard basis must be one of those. Polynomials are the only one that pick an extra dimension, because if you talk about a constant, right, constant will be like p sub 0, that's a, that's 1. And if you talk about, say, p sub 1, so a linear equation is really ax plus b, so you have 2 of those, and of course 2, that's ax squared plus bx plus c, and the list goes on. So you see you're adding an extra 1 vector every time. Now theorem 4.6.6, those are just gonna reinforce each other. They're not really that much different. Let V be an n-dimensional vector space, and let S be a set in V with exactly n vectors. So we're matching that. Then S is the basis for V if and only if S spans V or S is linearly independent. Now, if S is linearly independent, then automatically it's gonna pretty much automatically it's gonna span. And if it spans all of it, then that must be linearly independent because you covered all the vectors in there. Let S be a finite set of vectors in a finite dimensional vector space V. If S spans V but is not a basis, then S can be reduced to a basis of V by removing appropriate vectors of S. So you could have more vectors that wouldn't be bases because you already know that some of those are linearly independent. You could start reducing some of the vectors, keep all the linear independent vectors until you form bases. And the other way around, if S is a linearly independent set that is not already a basis of V, then S can be enlarged to form bases by inserting appropriate vectors in S. So for example, 1, 0, 0, 0, 1, 0. Those are linear independent vectors. I could add one more vector to that. And now this will span R sub 3. And that's what they're talking about. And the last part, they're talking about a subspace. This is a different game now. If W is a subspace of a finite vector space S, then W is finitely dimensional. That's fine. The dimensions of W is less than or equal to the dimensions of V, and W equal V if and only if the dimensions are the same. Now let's talk about bases and let's talk about how to find them. What we're going to do in this section, we're going to come back to in the following chapters and use over and over. They just have different names, but it's the same exact analogy. So I'm looking at problem number 2, and it states, find a basis for the solution space of the homogeneous linear system and find the dimensions of that space. If I put this as I mentioned, I could close it right there because there's nothing you could do to change those zeros, or I could write it like that, either way. And if I do the row operations and assume, actually I put those in the wrong order, but it's okay. If I reduce that, so something like that's going to happen on our next exam. This is going to be 1, 0, 1, 4, 0, 0, and this is going to be 0, 1, 1, 4, 1, 0. So if I look at this, keep in mind x1, x2, x3, x4. Now, I know that, and let's start getting used to that notation. x1 and x2 have pivots. So I know that x, and I know the book doesn't do this, we're going to start doing this anyways. We know that x3 is free and x4 is free, meaning we could call that S, we could call that T, whatever you want. It doesn't really matter. What matters is what's going to come next. So if I take x3 to be any value, I'm going to keep it at x3. I know the book uses S and T, and let x sub 4 be whatever it wants. Well, let's see. I know that x sub 1 is going to be negative 1/4 x3, and x sub 2 is going to equal negative 1/4 x sub 3 plus x sub 4. So if I kind of here, just reset this a bit. So I'm not going to be using this notation in the book. I'm going to go ahead and say x3 obviously is x sub 3 and x sub 4 is actually x sub 4. If you read the vectors, x sub 1 is negative 1/4 x sub 3, negative 1/4, a 1 and a 0. I know you're not going to like this in the beginning. You'll come around because this is going to come back over and over. And the next vector we got would be, so kind of like you fill in the blanks. 0, 1, 0, 1. Let me make sure. Yep, that seems to be correct. Just want to make sure I didn't make a mistake. 0, here. We said negative 1/4 minus when you move that over. So that is, there you go. Okay. So these vectors are linear independent since neither of them is a scalar multiple of each other, and we conclude that the bases, the v1, and call this v sub 1, v sub 2. Those form a basis for the solution space, and the dimension of the solution space is 2 for this problem. Now this solution space is going to be called many things. Later on, we're going to have a different name that's going to be very useful. We're going to kind of get used to this by doing 4 as well. And if I do 4, we're trying to figure out, so here, 1, 2, -4, -8, 3, 6, -1, -2. This one, I want to do the work. Actually, let me keep it. I don't know why I was going to put all zeros. Now, let me solve it. Here you notice with ease, if you take negative twice row 1 plus row 2, put the result in row 2, what would happen? Multiply this by -2 plus 2, that's 0, that's 0, that's -6, and that's 2, that's a 0. So what does that mean? That means I only have x. So again, let's get used to this and get it out of the way. This is something we're going to do for a while. So if I look at x sub 4 is free. X sub 3 is free. X sub 2 is also free because the only pivot is under x sub 1. X sub 1 is actually 4x sub 2 plus 3x sub 3 minus 3. And I'll show you again in case I'm not being clear how I'm getting that. So x sub 1, you're going to move that to the right, that to the right, and that to the right. That's why they have opposite signs. So look at the vectors that we're talking about. If I look at x sub 1, it consists of 4x sub 2, a 1 and none. It has -3x sub 3, no x sub 3, 1 and 0, and it has x sub 4, no, and a 1. So here we have 3 vectors. And if you're having a hard time seeing this, this is how I suggest you do it. When you say those are free, line them up. x2 is right there, right? x3 is right there. And there's x3. Just read those top to bottom. Right? This is x sub 3, this is x sub 4, and this is x sub 2, x sub 3, x sub 4, or any multiple will do. That's why we just write them as they are without the variables. Right? If I really wanted to be picky, I'm supposed to say, well, look, v sub 1 is actually x sub 2 times 4100. Right? V sub 2 is going to be x sub 3 times, well, look at the column of x3, -3010, and x sub 4, v sub 3 is going to be x sub 4 times 1001. But when you list them in there as a vectors, you just list the coefficients because any linear combination of those will do since they are linearly independent. So here the dimension of the solution space is actually 3, v1, v2, v3. And if I look at number 6, and I would go ahead and write as 1, 3, 4, 6, 1, 2, 3, 5, 1, -2, -1, 1. And what do you notice? What do you know is going to happen? That's 1, 2, 3 variables. And how many equations? 4 equations. If I really reduce this, well, it's clear. Let's do that really quick. Take -3r1 plus r2 in r2. Take -4 row 1 plus row 3 in row 3. And take -6 row 1 plus row 4 in row 4. So what would happen here? The zeros are untouchable. No matter what you do to this column, it's going to be all zeros. First round, multiply by -3 and add it to the bottom. That's 0. -3, that's -1. -3, that's -5 and a 0. -4, that's a 0. -4 plus, that's a -1. -4, that's a -5. Multiply by a negative 6, that's a 0. Negative 6 plus 5 is a negative 1. Negative 6 plus 1 is a negative 5. Do you notice that if I take now row 2 times negative 1, add it to row 3, put the result in row 3. Take negative row 2, add it to row 4, put the result in row 4, right? What would happen? So this one, let me work out very slowly. And let me see. Okay, there it is. That's a negative. All right. So here, what do we know? Well, here we know, look, there's a pivot. That's X. That's Y, right? So X and Y. We know that Z, this doesn't count. We knew one of those was going to zero out. We know that Z could be anything, right? Let's call it free. Well, let's see. This is the Z column. That means Y equal negative, so let this be Z. Y equals negative 5Z, and X equal negative Y minus Z, and we know Y is negative 5, so that's a minus a negative 5, that is 5Z minus Z, that's 4Z. So if I really want to get this right, this is how I'll do it. I'll list Z on the bottom, and Y would be negative 5Z, and X would be a negative Y minus Z. And if I list those as vectors, the Y, and what am I really looking at? I'm looking at, okay, so maybe I should put it here. That would be 1, negative 5, 4. So here the dimensions of the solution space would be pretty much 1. Okay. Now let's look at the next set of problems and work a few of those. In each part, find a basis for the given subspace of R4 and state its dimension. So here we found the basis for the solution space of this homogeneous system. I should have wrote the dimensions, huh? Here the dimension is 2, here the dimensions were 3, and here the dimensions were just 1. All right. Now, here we're going to take a subspace, find the basis for the subspace, and state their dimension. So if I take the very first vector, vector A, well, I'm looking at S, A, B, C, and 0. Well, A, isn't that really just 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0? That's it. And the dimensions of that is 3. So S form a basis for the subspace, and its dimension is 3. Well, that's because kind of like saying X, Y, Z, and 0, or X1, X2, and X3. I could write them like that. Now, if I go to the next problem, I notice, wait a minute, here they changed on me. Here's the form, but they really have D equal A plus B and C equal A minus B. So I notice that everything in terms of A and B. So here, let's say A, we call that, and again, put them in order, call that A. B, we put B right there. C is A minus B, and D is A plus B. Look at the A. Wouldn't you say that is 1, 0? Okay. That's the more appropriate. The A will be 1, 0, 1, 1. And wouldn't that be 0, 1, negative 1, 1? So there it is. Those are linearly independent, which means those will form the basis for the subspace, and the dimensions of this subspace obviously is 2. Okay, so we want to get used to writing those vectors in terms of each other. How about here? A equal B equal C equal, well, let's see. If I called A, and B I'm gonna call A, and C I'm gonna call A, and D I'm gonna call A. Hey, the dimensions of the subspace, this is the linearly independent vector, it's only one, so there's no other multiple of it. It is linearly independent, right? And the dimensions of this subspace is actually a 1. Now again, we should really practice this a lot, something that's never going to go away. Now I want to look at number 12. Find a standard basis for R sub 3. Find a standard base for R3 that can be added to the set V1, V2 to produce the basis for R3. Okay, what they have here on 12, they have -1, 2, 3, 1, -2, -2. They're saying figure out one more vector so that it will form the basis for all of R3. If you want to form the basis for R3, you need 3 linearly independent vectors that have 3 components each. All right? So let's see. There are multiple ways of doing this. Basically, you want to pick a vector, a third vector, and you want to check when you do the determinant of V1, V2, and the next vector, you don't get a 0. Well, let's see. If I take those vectors and I add those, I'll get 0, 0, 1. So the anchor here is the 1. I could choose either 1, 0, 0 or 0, 1, 0. As long as I don't touch the last one, it's fine. And as you can see, if I put 1, 0, 0 there, the determinant of this would be 1, and that is -4 plus 6, which doesn't equal 0. But there. And if you were to put 0, 1, 0 there, the same thing will happen. You pick the middle and you'll get a 2 minus 3, which is not 0. And there it is. So either of those two will do. Pick one of them, and that's that. And the same deal here. If I look at this vector, they gave me 2 of those. If I look at what they gave me, again, I want the determinant. To know that they're linearly independent, I'll have to check 1, -1, 0, 3. Of course, there are more answers because anything that allows the determinant not to equal 0 will work. But the simplest way, add them up. So that's 4, 0, and a -2. So this is a really quick way of choosing. But you could play here and figure out all the combinations that do that. So that's the determinant of that would be 1 times cross it row and column. That is times a -2. It's -1. So it's 2. Well, it doesn't equal 0. That's the important part. Therefore, yes, you could add this to those vectors, and that will form a linearly independent, that will form the basis for this vector space. Same thing here. You have those 2 vectors. Just add v sub 3 to be, in this case, we decided which one. 1, 0, 0 or 0, 1, 0 will work. Those 3, and here, just add to this list v sub 3, and we said which one. There are more choices than this. Kind of like when we said back in the days, find a vector that's orthogonal to another. Well, any combination of dot product that gives a 0 will work. We would like to find, those are 3 vectors, be a basis for a vector space V. Show that U1, U2, U3 is also basis where U1 equal V1, U sub 2 equal V sub 1 plus V sub 2, and U sub 3 equal V1, V2, V3. So this form basis for this vector space. Show that any linear combination of those will form basis as well, and it'll work out to be identical. Well, let's see. What we want to show, we want to show C1U1 plus C sub 2 U sub 2 plus C sub 3 U sub 3 equal, oh, I'm getting careless there. Well, isn't that C sub 1 V sub 1 plus C sub 2 V sub 1 plus V sub 2? And isn't that C sub 3 into V sub 1 plus V sub 2 plus V sub 3 equals 0? Or simply, let's see, if I take V sub 1, I'm multiplying that by V sub 1, C1 plus C sub 2 plus C sub 3. And if I take V sub 2, the coefficients are 0, V sub 2, not V sub, C sub 2 plus C sub 3. And if I look at V sub 3, that's 0 there, 0 there. It's only C sub 3. Again, all of these are vectors. So doesn't that mean I'm really looking at this system? Let's see, 1, 1, 1, 0. And what do you think the solution is? C sub 3 is 0, C sub 2 is 0, and C sub 1 is also 0. Oh, I'm sorry. You gotta forgive me. Multitasking is not something I could do. I tried multitasking many times and I mess up. If I'm trying to finish two things together, I mess both of them up. So I can't multitask at all. So I'm getting those, so that tells you that U sub 1, U sub 2, U sub 3 are linearly independent, right? Since the dimensions of V is 3 and its bases are 3, we know that any combination of those must form the bases as well for V. All right, this is kind of showing that it is unique if they match. Let me look at the next problem up. 16 is more straightforward. The vectors V1 and V sub 2, so they have 1, 0, 0, 0, 1, 1, 0, 0, okay, are linearly independent. They tell you that, okay, whether you put a 0 there or not, doesn't matter as long as that's 1 and that's 0. I don't know, you know what, I should really write the law slower. Here we go. Or even better. There we go. So here it's really easy to predict what you're gonna have to do. Enlarge this to form bases. I need 4 vectors. Again, the fact that this is a 1 and this is a 1 doesn't matter. You could put a 0 there. Any multiple of that will do. As long as that's the case, the easiest choice would be add those vectors, and I know for sure they're linearly independent. How do you know that? Well, let's see. 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Yeah? If I multiply row 2 by -1 and add it to row 1, that's pretty much make that a 0. Yeah? Actually, I don't even need that. This is a triangular matrix. Wouldn't that be simply the determinant will be a 1, and therefore those are linearly independent, right? So we conclude that, you could enlarge it by simply adding those two, and pretty much you're done. So if it's that simple, you really don't have to do a lot of work. Let me just move this up. Okay, on the following problem, find the basis for the subspace of R4. So we're going to figure out which of those are linearly independent and go from there. So if we take this vector times C1, this vector times C2, this vector times C3, this vector times C4, we're pretty much trying to solve the matrix of C1, they go this way. That's all of the C1s, the C2s, the C3, and the C sub 4. Let's see how this plays. Well, negative row 1 plus row 2 and row 2, negative row 1 plus row 3 and row 3, and negative row 1 plus row 4 in row 4. What that does, and of course we don't have to put that there, we could just see the reduction of them, but it's all good. So that's 0, 0, 0, 0. Okay, one of these zeroed out. And then that is 0, 0, 0. Oh, wait a minute. You could tell right away. And that one is 0, 2, 0, negative 2, right? 3, negative, and a 1. And now if you take, oh, there's not much to do. If I switch those rows, if I take row 4, switch it with row 3, I'm really looking at 1, 2, 0, 3, 0, negative 2, 3, 1, 0, 0. And from this, we see we only have 2 pivots. So pretty much find the basis for the subspace. Any linear combination of those will form the basis for the subspace of R sub 4. Basically, those two vectors span v1, v2, v3, and v4. So the basis for the subspace are the linear combination of those. That's really what that means right there. And last thing I want to do, 19 has A, B, C, D. I would like to do one of those just to make sure we know how to do it. And with a matrix, it's slightly different. In each part, let the transformation R3 into R3 be multiplication by A, and find the dimension of the subspace of R3 consistent of all vectors x such that TAX equal 0. So, well, let's see. If I take TAX, pretty much I'm trying to reduce that. So if I put the zeros right there, obviously if I take negative row 1 plus row 2, put it in row 2, take negative row 1 plus row 3, put the result in row 3. You know what, I should really start writing nicer than this and slower. Basically, well, I'll have 1, 2, 0, 0. So here I could say x sub 3 is free, x sub 2 is free, and x sub 1 is negative 2x sub 2. So I could say negative 2, 1, 0, and 0, 0, 1. Let me double check really quick. 2, 1, 0, 0, 1, 0. Okay, yeah, there you go. Those form metron. These are the bases. These are the bases for the space and the dimensions. Obviously, I don't know what you want to call them mass. And that's pretty much it how this section works.